Hi, in this video, we will discuss how to calculate the concentrations of hydronium ion and the hydroxide ion, and then determine whether the aqueous solution is neutral, acidic, or basic based on the said concentrations. Then we will also discuss how to calculate the pH and pOH of an aqueous solution and determine based on that whether the solution is acidic, basic, or neutral. Now suppose we add an acid and our base to water. The acid will give away or donate a hydrogen ion to water to produce a hydronium ion. Therefore, we can measure the acid present using the hydronium ion concentration. By the way, the square brackets represent the concentration. On the other hand, a base will accept a hydrogen ion, okay, from water, and that will result in creating a hydroxide ion. Okay, therefore, we can measure the base present in the aqueous solution using the hydroxide ion concentration. Now, experiments have shown that in pure water at 25 degrees Celsius, the concentration of hydronium ion is equal to the concentration of hydroxide ion, and yeah, they are both equal to 1 times 10 to the negative 7 molarity. Uh, on the other hand, in an aqueous solution with an acid and or a base, the hydronium ion concentration and hydroxide ion concentration are inversely related. Okay, and that relationship is given by this equation. So we have the hydronium ion concentration. If we multiply that by the hydroxide ion concentration, we get 1, okay, times 10 to the negative 14 molarity, which is a constant. So if we increase, the hydronium ion concentration, the hydroxide ion concentration should decrease. And if we decrease the hydronium ion concentration, the hydroxide ion concentration should increase. Based on the hydronium ion concentration and the hydroxide ion concentration, we have the following types of aqueous solutions. At 25 degrees Celsius, a solution is neutral when the hydronium ion concentration is equal to the hydroxide ion concentration, and they are both equal to 1 times 10 to the negative 7 molarity. In an acidic solution, the hydronium ion concentration is greater than 1 times 10 to the negative 7 molarity, and the hydroxide ion concentration is less than 1 times 10 to the negative 7 molarity. So in this case, we have more hydronium ion concentration. That's why the solution is acidic. On the other hand, for a basic solution, the hydronium ion concentration is less than 1 times 10 to the negative 7 molarity, while the hydroxide ion concentration is greater than 1 times 10 to the negative 7 molarity. So in this case, we have more hydroxide ions. So therefore, or so that's why the solution is basic. In this exercise, we have to determine which solution is more acidic based on the hydronium ion concentration. First, we have a solution with hydronium ion concentration equal to 3 times 10 to the negative 5 molarity. Okay, then we have a second solution with hydroxide ion concentration equal to 1 times 10 to the negative 6 molarity. Since we have to compare the two solutions based on the hydronium ion concentration, we don't have to do anything to the first solution, right? Because we already have here this one. For the second solution, we have to calculate the hydronium ion concentration from the hydroxide ion concentration. And the equation that relates these two concentrations is this one. So you have the hydronium ion concentration times the hydroxide ion concentration, that is equal to 1 times 10 to the negative 14 molarity. So we simply have to plug in the given value of hydroxide ion into this equation. Okay, so since the hydronium ion concentration is the unknown, let's copy that as is. Okay, plug in this given value. So that is 1 times 10 to the negative 6. Okay, equal to the constant 1 times 10 to the negative 14 molarity. To solve for the hydronium ion concentration, we have to eliminate this one from the left side. So it looks like we have to divide both sides of the equation by that number. Okay, therefore, the hydronium ion concentration is equal to 1 times 10 to the negative 14 divided by 1 times 10 to the negative 6. Okay, so let's simplify that. Let's calculate that. Let's input 1 exponent negative 14 divided by 1 exponent negative 6. So the answer is 1 times 10 to the negative 8 molarity. Okay, so now we can compare this with the hydronium ion concentration for the first solution, which is 3 times 10 to the negative 5. This is 1 times 10 to the negative 8. Since 10 to the negative 5 is greater than 10 to the negative 8, then uh, the first solution is more acidic. This time we have to determine which solution is more basic, okay, based on the hydroxide ion concentration. First, we have a solution with 5 times 10 to the negative 4 molarity hydrochloric acid, and another solution with a hydroxide ion concentration equal to 3 times 10 to the negative 8 molarity. So since we have to compare the two solutions based on the hydroxide ion concentration, we don't have to do anything to the second solution, right? Because we already have this one. For the first solution, we have to first calculate or determine the hydronium ion concentration from this concentration of hydrochloric acid in a K solution. So let's consider the chemical equation for the reaction of hydrochloric acid with water. So let's add water. Okay, this hydrogen ion or atom will be given to water because hydrochloric is an acid. That is to produce a hydronium ion. Hydronium ion. And the other ion is the remainder of the hydrochloric acid, which is Cl. Since hydrochloric acid is neutral, Cl should have a charge of 0 minus positive 1, so that is negative 1. Okay, now let's see if this equation is balanced. So you have one hydrogen, hold on. Uh, on the left side, we have one hydrogen plus two hydrogen, so that's three hydrogen. How many Cl? We have one. How many oxygen? We have one on each side. Therefore, this equation is balanced, so uh, we can conclude that to for 1 mole of hydrochloric acid, 1 mole or the same number of mole of hydronium ion will be produced. Okay, so again, okay, the hydronium ion has the same number of moles as the hydrochloric acid, and they are in the same volume or amount of solution. Therefore, we can conclude that the hydronium ion concentration is equal to the concentration of hydrochloric acid in aqueous solution, and that is given as 5 times 10 to the negative 4 molarity. Okay, we can now use this hydronium ion concentration to solve for the corresponding hydroxide ion concentration, okay, using the same equation that we used in the previous problem. So you have hydronium ion concentration times hydroxide ion concentration is equal to 1 times 10 to the negative 14 molarity. Okay, let's plug in the given the calculated value of, or yeah, the value of the hydronium ion concentration. So that is 5 times 10 to the negative 4. Okay, then we copy the concentration of hydroxide ions, okay, because that is the unknown, and again copy the constant on the right side. Okay, so to solve for the hydroxide ion concentration, we have to eliminate this number on the left side. So it looks like we have to divide both sides of the equation by that number, okay, in order to get the hydroxide ion concentration is equal to 1 times 10 to the negative 14 is rather over or divided by 5 times 10 to the negative 4. Okay, let's input that in the calculator. So you have 1 exponent negative 14 divided by 5 exponent negative 4. And the answer is 2 times 10 to the negative 11. Okay, again, that is 2 times 10 to the negative 11. Okay, so now we can compare that with this hydroxide ion concentration for the second solution. Okay, so we have here 3 times 10 to the negative 8, and for the first solution, we have 2 times 10 to the negative 11. Since 10 to the negative 8 is greater than 10 to the negative 11, then the second solution is more basic. This time we have to calculate the hydronium ion concentration or the hydroxide ion concentration. There are actually two problems, so let's divide the space into two. So we can do the part A on the left side. In part A, we have to calculate the hydronium ion concentration in 5 molarity potassium hydroxide solution. Potassium hydroxide is a strong base. So if we add that to water, it will dissolve and completely dissociate into its component ions, which are potassium and hydroxide ions. Now this is a balanced equation. So for 1 mole of potassium hydroxide, we will be able to produce 1 mole of hydroxide ions. So they have the same number of moles and they are in the same volume of solution. Therefore, we can say that the concentration of hydroxide ions is equal to the concentration of potassium hydroxide. And that is given as 5 molarity. So we can use this concentration of hydroxide ions to calculate the corresponding hydronium ion concentration using the equation that we have used in the previous problem. So this is equal to 1 times 10 to the negative 14. Let's plug in this this given value of the hydroxide ion concentration. So of course we have to copy the first one because that is the unknown, times 5 equal to the constant 1 times 10 to the negative 14. So to isolate or to solve for the hydronium ion concentration, we have to eliminate this one, okay, on the left side. So it looks like we have to divide both sides by that number. Therefore, the hydronium ion concentration is equal to 1 times 10 to the negative 14 divided by 5. Let's input that in the calculator. So we have 1 exponent negative 14 divided by 5. Okay, the answer is 2 times 10 to the negative 15 molarity. And that is the concentration of hydronium ions. In part B, we have sulfuric acid. So we have to calculate the concentration of hydroxide ion given 2.5 mole of sulfuric acid in 2-liter solution. Okay, so let's write the chemical equation for the reaction of sulfuric acid with water. So let's add that to water. Okay. Yes, one of the hydrogen, okay, in sulfuric acid will be given away to water to produce a hydronium ion. And the remainder of sulfuric acid is H. So we now have only one hydrogen, SO4. So that is the hydrogen sulfate. Since the sulfuric acid is neutral, the hydrogen sulfate, okay, has a charge of 0 minus positive 1. So that's negative 1. Now that is actually a balanced equation. So to produce 1 mole, no, for one given 1 mole of sulfuric acid, we will be able to produce 1 mole of hydronium ions. Okay, so they have the same number of moles and they are in the same volume of solution. Therefore, we can say that the concentration of hydronium ions is equal to the concentration of sulfuric acid. Okay, and we can calculate this concentration of sulfuric acid based on using the definition of molarity. Remember, we have to express the concentration in molarity, and that is the mole of solute over the liter of solution. We are given the mole of solute, that is 2.5 moles all over the liter of solution, so that's 2. Therefore, the hydronium ion concentration is 2.5 divided by 2, so that is 1.25. Okay, and again we have to we can calculate the corresponding hydroxide ion concentration using this same equation. Okay, so let's plug in the this value for hydronium ion concentration. So that is 1.25 times the unknown hydroxide ion concentration is equal to the constant 1 times 10 to the negative 14. Okay, so to solve for the hydroxide ion concentration, we have to eliminate 1.25 on the left side, so we have to divide both sides by that number. Therefore, the hydroxide ion concentration is equal to 1 times 10 to the negative 14, okay, divided by 1.25. Okay, let's input that in the calculator. So we have 1 exponent negative 14 divided by 1.25. And the answer is 8 exponent negative 15. Where's the pen? Come on, pen. Hold on. Let's wait for the pen to appear. Okay. Again, the answer is 8 exponent 15. Uh, Hold on. Okay, so again, the answer is 8 exponent negative 15 molarity. And that is the concentration of hydroxide ion. Now let's discuss the pH scale. In pH, the small letter p represents the negative of common logarithm of the hydronium ion concentration in molarity. When we say common logarithm, that is logarithm to the base 10. So when it comes to logarithm, the general form is log to the base a of b. So we have this base a. But if we don't see a base, that is actually 10, but we don't usually write it. Okay, so the formula for pH is negative log to the base 10 of the hydronium ion concentration, And remember that the concentration should be in molarity. Okay. Now, if we need to calculate the hydronium ion concentration from a given pH, we have to consider we have to use the inverse of this expression. So this expression is a logarithmic expression. The inverse of that is an exponential expression, which is this one. So the concentration of hydronium ion is equal to 10 to the exponent negative pH. Now, in the previous slide, we said that um, the concentration of hydronium ions in pure water is 1 times 10 to the negative 7 molarity. So if we need to get the pH of pure water, so we write negative log of that concentration, okay? And if we input that in the calculator, we should get exactly 7, okay? The pH level is used to determine the level of acidity or basicity, if there is such a word, uh, of an aqueous solution. So we have the following types of solution in terms of pH. For a neutral solution, the pH is 7. Okay, because for example, because an example of a neutral solution or neutral substance is water. Okay, now in an acidic solution, the pH is less than 7. Okay, and for basic solutions, okay, the pH should be greater than 7. Okay, in this exercise, we have to calculate, okay, the pH. Let's calculate the pH. Where is the pen? Okay, pH, okay, from a given hydronium ion concentration. Okay, so for this one, we simply have to use, okay, the formula for pH. So the question is, what is the pH of 0.75 grams sulfuric acid in 500 ml aqueous solution? Okay, so in this case, we are not given the concentration of the solution. So we have to calculate it first. And for that, we need the mole of solute. Okay, what we are given is the mass of solute in grams. So it looks like we have to calculate first the molar mass of sulfuric acid. Okay, let's do that. So in sulfuric acid, we have HS, then O, two atoms of hydrogen, one sulfur, and four oxygen. The atomic weight of hydrogen is, let's use three decimal digits, 1.008. For sulfur, it's 32.076. 32.076. And for oxygen, 15.999. So we can round that off to 16. Okay, so 16.000. Okay, so let's input that in the calculator. So we have 2 times 1.008, 2.016, 2.016. For sulfur, we have only one atom, so that is 32.076. For oxygen, we have four atoms times 16, 64. Okay, let's get the total of that for the molar mass. So we have 2.016 plus 32.076 plus 64. And the answer is 98.092. This is gram per mole. Now again, what we're given is, okay, mass of sulfuric acid in grams. So let's start with that. So we have 0.75 grams of sulfuric acid. Let's do stoichiometry. Okay, so let's multiply that by the reciprocal of the molar mass. So we have here 98.092 grams per 1 mole. Okay, that is to cancel the grams and to obtain a unit of mole. Okay, so let's input that in the calculator. We have 0.75 divided by 98.092. Okay, and that is 7.646. Okay, pen, where is the pen? Okay, 7.646 times 10 to the negative 3. Okay, that is the mole of sulfuric acid. So that is a mole of solute. Okay, so we can now calculate the uh, concentration of sulfuric acid in molarity. So mole of solute is 7.646 times 10 to the negative 3. Okay, that is negative all over uh, the volume of solution in liters. Okay, or in liters. So we are given 500 ml since there are 1000 ml in 1 liter. Therefore, this is equivalent to zero point 0.5 liter. Okay, so zero point 0.5 liter. Again, this is in mole. So let's input that in the calculator. 7.646 exponent negative 3 divided by zero point 0.5. So we have 0.015. Okay, so the molarity is 0.015. Okay, we now have the concentration of, this is sulfuric acid. Okay, so molarity of sulfuric acid. Okay, but remember in the previous slide, for 1 mole of sulfuric acid, we will be able to produce 1 mole of hydronium ion. So therefore, we can say that this is also the concentration of hydronium ions. Okay, so yeah, so therefore we can now use the formula for pH. So pH is equal to, remember, negative log to the base 10 of the hydronium ion concentration. Let's plug in, okay, the concentration. So we have negative log to the base 10 of hydronium ion concentration is 0.015. Okay, and that is equal to negative log to the base 10 of 0.015. So we have 1.82. Okay, 1.88824. Okay, so the pH is therefore equal to 1.824. And since that is less than 7, so this is a final answer, by the way, but since that is less than 7, then we can say that, oh yeah, of course, it is acidic because we have sulfuric acid. Now let's do the opposite of what we did in the previous slide. Let's calculate the hydronium ion concentration from the given pH. Okay, so we have a liquid sample with a pH of 8.3, and we have to calculate the hydronium ion concentration and the hydroxide ion concentration. So if we want this, okay, from pH, we have to use the opposite of, or rather the inverse of the formula for pH. And that is the concentration of hydronium ions is equal to 10 to the exponent negative pH. So we simply have to plug in this value for the pH. So that is 10 to the negative, again, pH is 8.3. Now, if we input that in the calculator, so we have 10 to the exponent negative 8.3. Okay, the answer is 5.01 times 10 to the negative 9. So 5.01 times 10 to the negative 9, and that is the answer to the first question, which is the concentration of hydronium ions. So that is a final answer. So let's indicate the unit molarity. Now we can calculate the concentration of hydroxide ions from the concentration of hydronium ions using the same formula that we have been using. So the concentration of hydronium ions times the concentration of hydroxide ions is equal to 1 times 10 to the negative 14. So let's plug in the calculated concentration of hydronium ions, so 5.01 times 10 to the negative 9 times the concentration of hydroxide ions, okay, that is the unknown, equal to the constant 1 times 10 to the negative 14. Okay, so to solve for the hydroxide ion concentration, we have to eliminate this number from the left side. So let's divide both sides by that number. Therefore, the hydroxide ion concentration is equal to 1 times 10 to the negative 14 divided by 5.01 times 10 to the negative 9. And let's input that in the calculator. So 1 exponent negative 14 divided by 5.01 exponent negative 9. And the answer is 1.996. So let's round that off to 2 times 10 to the negative 6. So the concentration of hydroxide ions is 2 times 10 to the negative 6 molarity, and that is a final answer. Now let's discuss the opposite of pH, which is pOH. Okay, uh, as in the case of pH, the small letter p represents the negative of common logarithm, or the negative of the base 10 logarithm of the this time the hydroxide ion concentration, but that concentration should still be in molarity. Okay, so we have a pOH. Okay, we simply have to replace the hydronium ion concentration by the hydroxide ion concentration. And if we need the concentration of hydroxide ions, okay, from a given pOH, we have to use the inverse of the logarithmic expression, okay, which is this exponential expression. So the hydroxide ion concentration is equal to 10 to the negative pOH. Okay, so yes, this equation relates, okay, the pH and the pOH. Okay, so remember that if we add pH and pOH, we should be able to get the constant 14. Okay, so this is a constant. Therefore, if pH increases, pOH should decrease. Or if pH decreases, pOH should increase. So, uh, similar to the relationship of hydronium ion and hydronium ion concentration and hydroxide ion concentration, the pH and pOH are also inversely related. Now this one is the same problem that we solved in a previous slide. So we have a liquid sample with a pH of 8.3, and then we have to calculate the hydronium ion concentration and hydroxide ion concentration. Again, if we need the hydronium ion concentration from a pH, okay, so we have to use the inverse of the formula for pH, which is the hydronium ion concentration is equal to 10 to the negative pH, right? Okay, so let's plug in the given pH. So that is 10 to the negative 8.3. And from the previous slide, this is equal to 5.01 times 10 to the negative 9 molarity. Okay, so that is a final answer for the concentration of hydronium ions. Now, for the hydroxide ion, we solved this using the formula relating the two concentrations. Okay, but this time, let's try to solve for the hydroxide ion concentration but using the relationship between pH and pOH. Remember pH, if we add that to pOH, Okay, we should get the constant 14. Okay, so let's plug in the given value of pH. So that is 8.3 plus pOH is equal to 14. So if we want to solve for pOH, let's transfer this one to the right side. So therefore pOH is equal to 14 minus 8.3. Okay, 14 minus 8.3 is 5.7. Okay, 5.7. Then from this pOH, let's see if we can get the same hydroxide ion concentration. In the previous solution, the calculated hydroxide ion concentration was 2 times 10 to the negative 6 molarity. Okay, so the inverse of the formula for pOH is, remember, the hydroxide ion concentration is equal to negative, sorry, not negative, but rather 10. Okay, 10 to the negative pOH. Okay, let's plug in the calculated value of pOH. Okay, so that is equal to 10 to the negative pOH again is 5.7. Okay, let's input that in the calculators. You have 10 exponent negative 5.7. Okay, and the answer is the same. Okay, so yes, so in this problem, okay, we can use the relationship between the hydronium ion concentration and hydroxide ion concentration, or between the pH and pOH, okay, to solve for the hydroxide ion concentration. And that's it. Thank you for watching.